Awesome. Okay, so yeah, I guess we'll probably get started. Seems like people are almost done filtering in. Yeah. Let's give us another minute, but yeah. And can people on Zoom hear me? Just like thumbs up or whatever. Oh, yes. Okay, awesome. All right, so yeah, today we are going to be doing like an introduction to PWN, which is okay. First, before we go into that, like announcements, we're going to be hopefully helping clean up ACM because the like exec team or whatever has bribed us with getting our own DDR area if we help them clean it up. So if you guys like Dance Dance Revolution, then you should help us. If you don't like Dance Dance Revolution, you should also help us so that you can play and then like Dance Dance Revolution. So yeah, those are like our DDR pads. Those are in the ACM room right now. I like built a like wooden bar thing for mine, and we're going to do that for another. You can probably help us like paint them or whatever as well at some point. So definitely like get involved with that. And yeah, so that's going to be on this Saturday when I will not be here, unfortunately, and then the Saturday after when I will be here to help. So yeah, do that. And then this is just the meeting flag. I'll give you a few seconds to count the number of A's. No, okay, there are 24 A's in the flag. So type that in. And then there's also our relevant XKCD for the week. This is, and it's about like the Heartbleed bug, which is a relatively recent, maybe kind of old bug now in a very popular library using a lot of stuff that was fairly simple in that it would just read arbitrary amounts of memory based on you sending it a number. And you could leak a lot of important stuff through that. And that might make more sense once we go over what PWN actually is. And so PWN is kind of, I don't know, kind of like a hacker slang term, I guess. And a more descriptive term for it is binary exploitation. And what this means is that your exploit is abusing the mechanisms behind how the compiled code is executed. So compiled languages, C, C++, I don't know, Rust, Go, all of these, compile down to machine code that gets executed on the processor. And so you're interacting directly with what the processor does with this data on or very near the hardware level, which is extremely cool. And it's also what is used the most in like, actual real world adversarial like hacking. Like if you have a company that is paid to hack other people in like a adversarial fashion, not like a we're going to help you secure your products fashion, probably what they're doing is binary exploitation. So this is like real cool stuff. Although we're kind of starting with stuff that was like state of the art in the 90s and is no longer that applicable. But still, this is like the building blocks to the stuff that actually gets used in the real world. And then this also means this stuff is hard. So definitely ask for help. If you think you understand it, definitely help other people. Got to be collaborative learning environment and whatever. So yeah. All right. So we're going to start with just an overview of what memory is when a compiled program is executing. And so a compiled program is just a bunch of numbers. You can see here, I hex dumped the cat program, which just like outputs files or whatever. And you can see it's just a bunch of numbers, and somehow these numbers translate, indicate that this program outputs whatever file you pass to it. And each number in the program, it's called a byte, ranges from 0 to 255. And it's stored at an address, which is basically, you can think of this like memory is basically just this giant array, this giant list with indexes from 0 to 2 to the 64 minus 1. And every byte is stored in an address within that range. Many of them are consecutive, and generally a byte in a program will have like one of two kind of purposes or meanings. It'll either be an instruction, which means the processor looks at this, and then this gets plugged into the processor's actual like hardware circuit that's inside of there to make it do something. So maybe it'll like tell it to use the adding circuit to like add two numbers, or like maybe it'll tell it to read an instruction from a different address. And then there's also like the data, which generally has some special meaning that is defined by what the program's doing with it. It might be that this byte is like that is only part of a larger number that consists of like a whole 8 bytes or something, or it might indicate a letter, or it might indicate a part of a memory address. So, and generally, yeah, I don't know, like I said, it's kind of that. And this is the layout. that most programs or the programs we'll be looking at have. And this is generally what happens when you compile, C or like C++ too. Generally, you have your .text section, which is where the instructions, as we talked about, are stored. So this is the data that is generally not changing during the program's execution. It's just there, and it's telling the processor what to do. And then you also have a lot of sections for data that can change. There's .data, .bss, heap, and stack. All we're going to care about during this lesson, I guess, is the text section and the stack section. So text is storing the instructions, as I said, and then the stack is storing like runtime data. So it's storing data that is, being allocated kind of dynamically for, whatever procedure, whatever function is executing right now. And we're going to look at how this actually looks when you are calling functions and stuff. And here, stack is generally stored towards the top of memory. And then the .text is generally stored towards the bottom of memory. And so generally, like the kind of old school terminology for this is smashing the stack. There's like some popular like magazine article or like hacker zine article called like Smashing the Stack for Fun and Profit or something back in like 1996. That kind of was the first to really publicize the technique we'll be talking about here. And for a long time, this was like a thing where you could hack a lot of programs with this. Nowadays, it's a little harder, but you'll learn about that if you attend more meetings. So yeah. So first, just the stack. So when we call a method or call a function like method one, the way the stack is laid out, when you call this, like the method one would be called within another function, right? Like maybe it's called within main. And then you push the parameters. So you have A, B, and C. Those are the parameters to the function. And then you have your return address. We'll talk about why that's a thing later. You have your saved frame pointer. If you attended like the reversing or the assembly meetings, you might understand why that's a thing. But it doesn't really matter for this. Just know that there are 8 bytes there. And they are necessary for the program to function, but not for you to hack it. And then finally, above that, you have your local variables, which can be of any length, but will indicate like a single like table cell here is going to be 8 bytes. So let's look at how the stack looks in an actual program. So we have a main function here. That's what it's called when the program executes. Within that, we call this vulnerable function, which takes a single argument, A. It doesn't do anything with it, but this is just to demonstrate. When we call this function, that argument gets put on the stack. And then the return address gets put on the stack. And this is an address inside main. And we'll talk again about that later. You have your saved frame pointer, which we aren't really going to delve into. And then you have your allocated stack variables. And here you can see we have stack var 1 and stack var 2. And they are kind of in reverse order. Stack var 2 is on top, stack var 1 is below it. And what this function does, you can see so it's an array of characters if you're not familiar with C syntax. And it's 8 characters long. Yeah, wrong way. There we go. Character, 8 characters long. Each character is a byte. So that's why these remain like 8 bytes long. And then you could have gets, that stands for get string. That's going to read a string from the user into the buffer stack var 2. And then you have put string, which is going to print out the buffer stack var 1. And so does anyone know what this program will do if you execute? If you just type in a couple characters, hit enter. It'll just print out an empty string, right? Because, well, okay, it's undefined behavior. But if this said equal 0, it would print out an empty string because this is initialized to 0. And then it'll just see a null byte and be like, oops, the string's over. However, gets is actually a dangerous function that the official documentation says never use this function. However, it turns out in the 90s, people did not realize this, and they did use this function. And even nowadays, maybe in some like embedded scenarios or something, you might find people using this function for some reason, or people using super old libraries from like the early 2000s. But yeah, so, and why should we never use this function? Well, because it reads in an arbitrary amount of user input. I guess first we should talk about like what a string is exactly and how that translates into what we discussed about memory being, right? So memory is just a bunch of numbers, whereas gets is reading a string. Well, the way this works is ASCII encoding, which you might have heard of, maps from bytes, so numbers from 0 to 255 to letters. So for example, the capital A is like 65. So if I type capital A into this program, it will store the number 65 in memory. And so gets can actually read arbitrary numbers from 0 to 255. It's just a little harder to input them if they aren't like something you can press on your keyboard, but we'll get into how to do that later. But the key idea here is that gets will read as much data as you type in, but generally in C, you will have a fixed amount of space to read into. So here you're calling gets on stack bar 2, and you have 8 bytes allocated, but you can type in as many as you want. And so let's think about what happens if we enter this. 8 A's followed by 7 B's. Well, gets, so the 8 A's, where do they go? They go into stack bar 2, right? Because that's the address we're passing to gets, and it's writing like 0, 1, 2, 3, blah, blah, blah. The B's, well, gets just keeps on writing. And even though we only ever passed in the address of stack bar 2, stack bar 1 is right below it in memory. So it's going to keep on writing into stack bar 1. And now, even though we never modified stack bar 1 in our code, because of like the underlying mechanisms in how this code is compiled and how it works, it's going to print out 7 B's. And this is kind of the fundamental idea here, is that you have the stack can be smashed, it can be corrupted when people use dangerous functions like gets. And we're going to see like cooler things you can do with this as well, I guess. Does that make sense to everyone so far? Yeah. Yeah, so gets is like another function, right? And what it does is it writes bytes into whatever address is passed to it. When you pass stack bar 2, what is happening in like the underlying code is stack bar 2 is just an address to memory, pointing right here. And so stack bar 2, so get sees like this address, like call this like address, I don't know, 80. And then it writes the first thing you type to address 80, writes the second thing you type to 81, etc. And then it hits address 87, and stack bar 2 is over. There are only 8 bytes in stack bar 2, right? So then it just overflows into stack bar 1. Does that answer your question? Cool. Awesome. Yeah, so here's just kind of explicitly showing you have the 8 A's that end up in stack bar 2, and then the 7 B's that end up in stack bar 1, even though we only ever explicitly said we're writing into stack bar 2. So that's like cool and all. We can modify local variables in a function, assuming it's laid out correctly on the stack. But what if we want to like jump around to other code that is not in the function we're executing? Or like, I don't know, what if there's like a admin only function that we want to execute that, I don't know, prints out a flag that we can submit for points on our internal CTF? Well, it turns out there's this nifty thing that I've been kind of skipping over called the return address. And I guess first we should go over kind of why this is a thing. So every time you call a function, functions are stored in the text section, right? I said that's where the instructions are stored in the program, and each function is stored in a different location. So when I'm in main and I call vulnerable, it's changing, the processor is changing where it's like executing the code, what address it's reading, to a totally different place in the program. And it has no obvious way to know where it's supposed to go back when it's done with this, when it hits this return statement. So the way it deals with that is it stores the return address on the stack, the return address being whatever the instruction is to execute after this function is done executing. So here, when vulnerable is done executing, it'll have the address of this puts call right in this return address thing. So when it hits this return thing, it'll know I'm going to jump to here and read the instructions from the address that references this code right here. And yeah. Does that, I guess, again, make sense, or questions? Yeah, so basically main gets translated into a series of bytes, right? These bytes tell the processor that it can do like the main, to do the stuff that main says to do in this higher level language. And some of these bytes mean call puts. And after you call vulnerable, you want to call puts. So it'll be the address of the bytes that tell the processor to call the puts function. I guess if that makes sense. So Thomas set up this thing last year that I think is kind of a fun analogy. So like about what return addresses are and what overwriting one can do. So, first Thomas enters his apartment. The program's beginning a new function. He's very happy. Life is good. Now he decides, okay, I know where I want to go after I'm done with my task in this room. I want to go back out to the hallway through this door. Yeah, you know, and he like notes down, okay, this door leads to the hallway. That's where I'm going to go. And then, you know, he does his task, he vacuums, he eats cereal, or, you know, simultaneously, maybe, I'm not really sure. And he does that to completion, but someone, meanwhile, with like whatever's been going on, has manipulated his like memory, his stack, and oh man, it leads to the nether now, you know, and that's what happens when you're like overflowing. That's kind of what the program sees, I guess. So looking at this in an actual C program, so you have your vulnerable function that's going to get called in main. You have your char array, char array, as we've had before. You have your saved frame pointer, which we're not going to delve into, and then you have your return address, which is going to point to wherever vulnerable, the next statement after wherever vulnerable is called. And you know, we type in, let's say we type in this. Oh, and also win. This is going to be our target function that we want to call, pretend it's like some admin function or something that we want to call without actually having the permissions to call through normal usage of the code. It is stored at address 8044232 in the text section of the binary instructions. So we type in 1, 2, 3, 4, 5, 6, 7, 8 A's. We type in 8 B's, and then we type in this thing. This means \x32 means we're typing in the byte or the numbers 0x32, whatever byte that represents. Same thing, 42, 04, 08. And you can't type in 04 and 08 and 00 with a keyboard. You probably can type in 32 and 42. I think 42 is like capital B. But these ones you can't type in with the keyboard. We'll talk about how to input those later. But you type these in, and let's look at what happens. Stack bar 1, AAAA gets written. The base pointer thing, BBB, gets written. The return address gets overridden with this, the address of win. And now when the function, when we hit this return statement, it will, instead of going, you know, back to the hallway, it'll go to the nether, or like this win function. And yeah, that's kind of the idea of overriding return addresses. And I guess for the rest of this, I'm mainly just going to talk about like, there's a lot of weird quirks or like technical stuff you have to know, or like, I don't know, methodologies for actually writing and delivering exploits. So number one is little endianness. You'll notice here, this address is a bunch of zeros, then 80442 or 08044232. Whereas here I wrote it as 32420408 and then a bunch of zeros. This is because in x86-64, for some weird reason, numbers are a little endian. I'm pretty sure this is just kind of an arbitrary decision by the architecture, but this is how they're stored. And what this means is the least significant, or like the littlest bit, is stored first in memory. So if you're storing the number 1122 blah 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 88, it's going to be stored kind of backwards byte-wise. So you're first going to have 88, then you're going to have 77, then you're going to have 66, 55, etc. And the reason this is like least significant byte stored first, well, 88 is the least significant byte because in this number it means 0x88, which is like not a very big number. Like consider this to be a base 256 number where every pair of like numerals here is a digit. The first digit is actually contributes the most to like the magnitude of the number. It's 0x11 times 256 to the 7. So it's like very significant. It's the most significant byte. This is the least significant byte. The less significant the byte is, the earlier it goes in the little endian representation, if that makes sense. Now, here we just kind of commented in the address main is at, but you know, programmers aren't actually going to comment the address they're at. They aren't even really going to know where the compiler is going to put it. You have to get that from the compiled binary, and this is how you do that. You can do it in a couple of ways. If you're familiar with GDB, you can just open it up in GDB. I think if you went to the Rev meetings, you might be familiar. And you can type addr or address, and then the name of the function, and it will print out what address the function is at. You can also do it with objump, which like dumps a bunch of information about the ELF and the code and stuff. So you objump -d and then the binary name. And also important distinction, these are the binaries, not the source code. So you'll see like in the challenge files, you'll see like a .c file and like a just no extension file. You want to do this on the no extension ones. And then you can grep for the function name, in this case main, and you'll see the address and hex right there. And that way you'll know what to overwrite the return address. Generally, you'll want to search for like win or print flag or whatever function you see in the code that does the thing you want to do. So I mentioned that to do this exploit here, we have to type in these bytes, but we can't type them with a keyboard. We can do that with the echo command and then piping it in. So echo just echoes whatever you put past as an argument to it. It is like a bash command, like if you're on the command line, you type echo and then you type whatever and it echoes it. There's also this flag -e that enables escape codes. And that's what the syntax I used back there was, \x, and then 2 hex digits to indicate the byte that you want to output, the number that you want to output. So echo-e 01, 02, 03, 04 is going to output the byte 01, the byte 02, the byte 03, the byte 04, not these literal characters. And you can pipe this into the local binary and also into the remote netcat to run your exploit. And you can use this if your exploit is the same every time. I think for these challenges, that is almost always the case, especially for the earlier ones, the ones that like everyone should be trying to do. In later pwn meetings, we might get to ones where you have to use pwn tools. This is good to learn right now anyway, if you want to, or if you've used it in previous meetings. Here you can interact with it programmatically, and you can actually, send stuff like that. These slides are in the slide channel if you want to reference this code when you're doing stuff. Here, there's also the P64 function that will automatically little endian encode an address. So here you have this win function address. This will turn it into the BB AA0408000000 for you. That's convenient. So that's like the bulk of the meeting. I have a couple little like bonus things just to talk about, relatively like simple alterations that are you can play around within some of the challenges if you get through like the first 3 or so. So number 1 is integer overflows. So in C, I talked about how like buffers and stuff and memory is generally allocated to be a fixed size. Integers are the same way. Like the int type is only 4 bytes. You can't store that many numbers in 4 bytes. The maximum is 2 to the 31 minus 1, the int type, because it's signed. The minimum is like negative, something close to that, negative 2 to the 31 maybe. And so you see here, if I run this C code, print, I'm printing this number, these two multiplied, well, that should be like a big number, right? But instead I get a really small negative number. That's because I went over the maximum allowed, maximum representable number, and it wrapped around. So there's a challenge that kind of lets you play around with this idea as well, integer overflow. Fairly simple, but you should definitely try it out to kind of get an idea of how this works. Also, we've been talking about 64-bit binaries. We were talking about how all the addresses and stuff are 8 bytes. 32-bit binaries are kind of older. They're mostly used nowadays in like embedded stuff. Like for example, Macs just don't support 32-bit binaries period anymore. But it's there. We do have like a suite of 32-bit challenges as well if you finish the 64-bit ones, and they have some more complex ideas as well. So check those out if you have time, I guess, or at home, when after the meeting. The next couple meetings are, so this Saturday is the first ACM cleanup session. Please do this because I want to play DDR whenever I want with minimal effort, and you should too. So, and also if you ever want to like get into DDR, also like the rec room, you may know they have a DDR machine, but this DDR totally free, open 24/7. So do that. And if you ever want to get into DDR, like message me, or like, I don't know, Michael might want to help people. Michael is extremely good at DDR, better than me. Yeah, very fun, highly recommended. And then this Sunday, Thomas will be talking about ethics, which is always exciting. So you know what not to admit to doing. And then next Thursday, we'll be doing cryptography with, I guess, Hassam and Anakin. So that'll be a blast. Yeah. So yeah, we should start doing challenges. Here's the meeting flag again. This time I'm going to actually force you to count if you didn't hear the first time. Start with these 3 challenges, just to stack overflow but specific, and Brett to win in the Pwn 1 category. Everyone should be trying to get these. Definitely ask for help and everything. Ask people around you if you're struggling. And then we have a bunch of other challenges for you to attempt. Integer overflow. I talked about integer overflows. It's just that concept. And then some 32-bit stack challenges as well. Some later challenges also deal with shell coding, which I did not cover here. But if you went to the assembly meeting, you can probably, I think this past Sunday, you can probably grasp that relatively quickly. You can reference last year's slides where they did actually talk about shell coding. So yeah, get working, I guess.